questions after last time? Is everybody happy with the n-cube time algorithm for finding the convex hull? Okay. So the n-cube algorithm, going over this algorithm quite quickly. This algorithm said, hey, I can pick a set of n-square canonical lines. What does it mean? Not every line in the plane had the input of my endpoints. I want to check which lines are interesting. Interesting which means that all the points are either on this line or on one side of this line, because this line contains an edge from Pi to Pj. It contains an edge of the convex hull, obviously. So we will do the same, some idiotic, but mental gymnastics that we are doing with many algorithms in computational geometry. It looks like there is a set of infinitely square, if there is such a thing, many lines that we need to check, namely we can see continuously move the line up and down and left and right until something interesting happens, or we can decide ahead of time on a discrete set of lines that it's enough to check only these lines, namely all the lines that go through some point pk to some point pl. These will be the only lines that I have to check. It is only this discrete set, and that would be my starting point of the algorithm. So I'll pick a pair of points, pi, pj, pl, pk. I'll generate the line for this pair of points, and now I'll check every other line if every other line is either on L or on the same, they all on the same side of L. How? I remind everybody, we check the sideness. We want to ask if I'm going from Pi to some other point, Pi to PL back to PJ, did I make a left turn? And the answer should be yes to all the points, or the answer should be no to all the points. And once we find a line where all the points of my set are all on the same side of the line, I figure out that this line contains an edge of the convex hull, and just continue finding all these points. Furthermore, I'll direct all these edges so they are all pointing all counterclockwise or all pointing clockwise. So when I'll generate the convex hull, I'll essentially generate the points of the convex hull. Let's rename them as V1, V2, V3, V4. That is, everything needs to be in a counterclockwise order. And that's already a good example of all the headaches that we are saving to ourselves from once we are using the general position assumption. That is, that if the input is nice and we don't need to worry about 3 points that are collinear, then this algorithm is correct. It still takes order n cube, by the way. N cube, why? Because there are n square many pairs of points, n choose 2 to be precise, and for each of them I need to spend linear time to check each and every line. But in n cube time, I can figure out what is a convex hull. The headache that starts to appear with the assumption that there are three possible lines, three possible points on the same line, is first you'll figure the test will be, unless you pay attention to this case. I'm not trying to say that it's an intellectual challenge, trying just to say you need to pay attention or else bad things can happen. What are bad things? You might, turns out that the algorithm will decide that both CB, BA, and AC are all on the edges of the convex hull. That's bad, but that's just mildly bad. What could be worse is that the algorithm, because of numerical issue, remember, 3 points that are almost collinear might appear as collinear, and 3 points that are collinear might appear as not collinear, but is this a right turn or left turn? Both answers are legit. So what can happen? The algorithm will decide, for the case of 3 collinear points, that CB is not an edge of the convex hull because A will look as a right turn. Similarly, AC is not an edge of the convex hull, nor BA is not an edge of the convex hull. The third point will cause the test to fail when we'll check with a third. That is, once we'll collect all the edges of the convex hull, you'll figure out that suddenly an edge is missing, and what you thought is a legit convex hull suddenly has an area that is missing. And that's definitely a possible outcome of the algorithm if you are ignoring this type of cases and thinking that you have infinite arithmetic of all your computation. All your computation don't suffer from floating point arithmetic that still use only 64 or so many bits. Okay. Now, convex hull has plenty of applications. I'll ask you in homework 1 to answer on several of them, and here is one of them that I wanted to show you. I have a convex polygon. I'm given a convex poly n-gon, so n is a number of edges, which is also the number of vertices for this polygon, and just call it n-gon, namely P, and I can pre-process it, meditate, think about its vertices. In this case, the pre-processing is not too bad. If the polygon is given, it's only linear time, such that given a query point Q, when you'll tell me about a query point Q, you'll give me the X and Y of a query point, I'll be able to answer quickly in log n time, is Q is inside this polygon or not. Okay. What's the rule of the game? You're going to bombard me with a lot of input points, and for each one of them I want to be able to answer quickly is P is inside the polygon or not. Okay, and there are another few key terminologies that I wanted to introduce you to, so I'm using it on this slide. So what are we going to do with this polygon? The assumption is that the convex hull is already computed, or maybe it's just a polygon that are given based on the list of vertices along its boundary or the list of edges along its boundary. In 2 dimensions, it's pretty much the same thing. And your first attempt in the pre-processing, in the part where you meditate, you prepare your data structure, first we'll find what is the rightmost point and the leftmost point. And if we assume general position assumption, which essentially we are just slightly rotating it, slightly introduce a bit noise. So these extreme cases don't happen, redundant cases don't happen, then if I have a vertical edge and I just slightly perturb it, one of its vertices would be slightly to the right comparing to the other. So I can assume that the leftmost vertex and the rightmost vertex are unique. It's a unique vertex. There are no 2 points which are both the leftmost points. Again, note that it's intellectual challenge to handle the case that you don't have general position. You cannot apply the general position assumption, but it just takes extra explanation and extra check if this is the case. So for my explanation now in the very high level, I will assume that the input is in general position, so the leftmost point is unique, the rightmost point is unique, and now I want to partition, wanted to introduce you to this notation, the boundary of P. We're using the partial, the D sign from partial equation. Here we are using it to denote all the points on the boundary of the polygon. There is the polygon is all the area in between, and the fence that separates the polygon from the outside world is the boundary of the polygon. And I want to think about the upper convex hull and the lower convex hull of the polygon, the lower part and the upper part. Here are the vertices of the lower part. If in general you'll give me a convex hull, again, lower points are unique. The upper convex hull will be the roof of the convex hull, all the edges which are, you'll see if you stand at plus infinity and looking downward, but stop the rain, and the remaining edges are the lower convex hull, CH, convex hull. So here are the vertices that are all on the lower convex hull. Notice that U1, the first vertex, and the anonymous vertex over here, U6, I think, they are also in the upper convex hull. Okay, but general position assumption now at least prevent me from trying to decide if a vertical segment belongs to the upper or to the lower. Okay, so I'll assume that every edge is either on the upper or on the lower convex hull. And now I relabel the vertices, just think about them as with different names, so that U1, U2, U3, they are sorted from left to right. And same goes for the vertices on the top, they are also sorted from left to right. And my data structure is just put these vertices in an array in this order. The array that I'll use in this example will consist of the vertices U1, U2, U3, U4, U5, and U6, in this order, from left to right. And now you're giving me a query point. Only right now you surprised me with the coordinates of a query point Q with coordinates x0, y0, and I need to answer quickly if Q is inside the polygon or outside the polygon. And I'll do it in a very methodological way, step by step. You can definitely shortcut some of the steps that I'm doing here. I'll think about the vertical line L of all the points x such that x equals to x0. This is a vertical line that looks like this, going through Q, has the same x coordinate of Q, and this type of notation is just a shorthand of writing L, which are formally all the x and y, all the points in the plane such that x equals to x0. x0 is a x coordinate of the query point. This is just this vertical line of the point such that x equals to x0. And my goal right now is to ask, hey line, do you cross any of the edges of the polygon? Because if you don't cross any edges of the polygon, then obviously Q is not in the polygon. Q is possibly completely to the left of the polygon, completely to the right of the polygon, but definitely not anywhere in a place that allows it to be inside the polygon. Think why. So if Q is inside the polygon, then my line L needs to cross general position, two edges, one in the top, one at the bottom. Again, ignoring the case right now that this line goes exactly through a vertex. What am I going to do right now? Looking at the x coordinate x0, looking at the x coordinate of all the points inside the array, all I need actually are just their x coordinate, and I'm using binary search, performing search of x0, and if x0 is not in this array, then what I'll get is an index such that the element just before it is to the left of u0. That is, I'll get the rightmost point which is to the left of L, and I'll get the leftmost point which is towards the right of L, which tells me that the edge connecting them, the edge connecting these two vertices that my search ended with, these 2 points are the edge connecting them must be crossed by L, because one point is just to the left of Q and one point is just to the right of Q. These are the two most similar points among the points in the lower convex hull. Remember, I'm doing this exercise for the lower convex hull, and now I find this edge. I can ask, hey Q, are you above this edge or below this edge? How do I answer above or below? Once again, performing my funny formula as before that tells me is if I'm going from U4 to Q to U5, did I turn clockwise or did I turn counterclockwise? Right? Have I, when I'm going from this, when I'm going from U4 to Q to U5, if I'm driving along this way, did I have to turn my steering wheel to the right, or did I need to turn my steering wheel to the left, which will be the case if Q is below the edge U4, U5. Okay, and now I repeat the same exercise with the upper convex hull to find the edge which is of the ceiling, which hopefully is above Q, and only if Q is above the edge in the lower convex hull and below the edge on the upper convex hull, only then I can conclude that Q is inside the polygon itself. What takes time? What is the only thing that takes time out of it? Well, I had to prepare all the vertices in the arrays that you see above me, but they are, if they are along the convex hull, they are already sorted, maybe counterclockwise, maybe clockwise, whatever it is. I don't really have to copy them. I can just look at any array that contains all the vertices in a sorted order. For conveniency, I can copy this array into two new arrays. One will contain only vertices of the lower sorted left to right, and same for only the vertices for the upper. Sorting doesn't take any time. Now, how much time did it take to perform the query? Well, I did binary search on the lower convex hull that contains at most n vertices, so it takes log n. Right? There are at most n vertices of the polygon in the lower convex hull, so it takes order log n to do the binary search on the lower convex hull, and the order log n to perform the search on the upper convex hull. Okay, that's now, of course, if you have a lot of points Q, there are tons of heuristics that you can throw into it, such as ask first if Q lies in the bounding box of the polygon before you're actually doing this search. Asking if Q is inside the bounding box is usually much faster, and only if Q lies inside the bounding box, then check if Q is inside the convex polygon or not. But there are plenty of other questions that uses similar ideas of binary search, and I'll let you play with it more in the homework. Okay, let's continue with algorithms for finding the convex hull. Why? Because they are good introduction to computational geometry, and they'll help us play with a few ideas that are shared with fundamentals of any textbook of algorithms as well. So I'm covering both corners of fundamentals to algorithms in general and introduction to computational geometry, and there are cool algorithms to mention all over. Okay, so I want to look to find the convex hull not in order n to the third, order n cube, what we have seen so far. Instead, I want to do it in order n log n, that, as we'll see, is more or less the optimal. So to do it, I'm going to apply Graham's scan. So our input is a set of points, p1 ... pn, all in 2 dimension, and the only thing that takes n log n in this algorithm would be sorting the points. Namely, I'll sort them from left to right. And my job right now is to compute the convex hull of the set, but I'll start by computing the upper convex hull, what we just saw in the previous slide. Only the ceiling of the convex hull is what I'll compute first, and then I'll run the algorithm again to compute the lower convex hull, the floor of the convex hull. And this is a really, really cool algorithm to my taste, and that's how it goes. I'm going to maintain the upper convex hull, but not of all the points. I'll always contain the upper convex hull, but only the point from P1, P2, P3, all the way not up to Pn. Pn is the rightmost one, P8 in this case. I'll only go up to Pj. So assume that by induction, I already computed the upper convex hull of all the points up to Pj, and Pj is the last point that I processed. And next, I'm going to add Pj plus 1. Remember, points sorted from left to right. I'm going to add one more point, Pj plus 1. And I need to decide if the addition of Pj plus 1 changes in any way the upper convex hull. And what we are going to do in general would be to ask, hey, if I'm going to add Pj plus 1, does it cause a right turn in the last point that I processed, or does it cause a left turn? Because if all my points are all on the upper convex hull, but think about it. If all my points Pi are all the upper convex hull, then what happens as I'm driving along the upper convex hull? Every time when I hit a vertex, I'm turning to the right, turning to the right, turning to the right in each and every vertex. It's also safe to assume that P1 must be on the convex hull, for sure. The leftmost point is always on the upper convex hull and always in the convex hull itself. It's the next point that I'm worried about. So let's assume that P2 is also in the convex hull, and what I'm asking is, when I'm going from P2 to one more point that I'm adding, P3, did I turn right, which is a good, because it's a good sign that P2 is, it doesn't tell me one bit about P3. I'm wondering about P3, I'm adding P3, but the point that I'm worried about is P2. The addition of P3, does it cause, is this an indication that P2 should or should not be in the convex hull? And in this case, you see that at P2 I'm turning right, so as much as I know right now, P2 is fine to be on the convex hull. Let's continue. Next to be inserted is P4. And when I'm adding P4, it's also in the, I'm also on my way from P2 to P3 to P4. I'm also turning to the right, but more gently in this case. So as much as I know, P3 is in the upper convex hull as well. I don't know about the future points yet. Here comes the interesting point. Now I'm inserting P5. I get to insert P5. And when I'm meditating about P5, I still have no idea about P3. P3, as much as I know, might or might not be on the convex hull. Who might be removed? Where do I have any point at which I turn left? Definitely is not on the upper convex hull. If I'm adding P5 and because of it, on my way so far, I had to turn left. The moment that I need to turn left, I don't know about any other point, P4 should not be there. Indication, P4 must be removed from the upper convex hull. Now, it will have another chance about the lower convex hull. For the lower convex hull, it's still an open game. P4 will have its chance to be on the lower convex hull. But as far as the upper convex hull, P4 should not be there. So, and the elegancy of the algorithm tells you you don't need right now to check each and every point in the history. You don't need to scan all your history. You just need to think about the very last point that you inserted. This point is the one that needs to be removed. So let's remove it. And now let's think about the new upper convex hull. And there is a left turn, but who is the one that caused the left turn? It's only the newcomers plus the very recent point up to the newcomer. Again, a left turn. Left turn implying P3 should not be on the convex hull. Don't know about the rest. Let's remove it. What happened right now? And at this point, I can tell you I'm always checking the last 3 points, and the data structure that is going to help me use all of it is a stack. Stack is going to implement everything very fast and very elegantly. Finishing with this example, at P2 turning right, at P5 turning right, the next point to be inserted, going from left to right, P6, meaning at P5 I turn right, safe to continue. From P6 to P7, oops, turn left, P6 should not be there. Let's delete it. At this point, I'm turning right, safe to add P8, but P8 caused P7 to be deleted because I'm turning left. Let's delete P8, P7, and voila, at all my turns, I'm turning to, on my way from P1 to P8, I'm turning right, implying that the green thing is the upper convex hull. Okay, so far, the only rule that is clear out of it is the following rule. I want to find the upper convex hull. I also want to find a black marker. Assuming that here is some simple, meaning intersection free. Polyline, polygonal line, polyline. And it starts from leftmost to rightmost. From the what is P1 on the slide all the way to a P8 in the slide. Let's think about every such polygonal line, and as I'm walking along this polygonal line, you don't know ahead of time if which points are in the upper convex hull and which points are on the convex hull, or on the lower convex hull. So I'm not telling you anything positive about a point that for sure will be in the upper convex hull. Well, P1 will be, P8 will be, because they are the upper and lower one, but for other ones I'm not sure about a yes condition, but I'm absolutely sure about a no condition. If on my way I'm turning to the left, then this point should not be on the convex hull, meaning that I can shortcut through it. The order doesn't matter. Every time that you are saying along this polygonal line a vertex at which you are turning a vertex at which you are turning to the right, coming from here and turning all the way to the right to reach this vertex, this should not be on the upper convex hull, so just shortcut through this vertex. And you can just keep repeating this process in any order you want. The order that you are going to apply this operation of filtering out vertices, this order will not influence the final result. The order will not influence the final result. However, using this clever trick with a stack, we are getting to a simpler way to check who is yes, who is no. So let's see how it goes. So we are using a stack. Stack, as you know from a 345, is a data structure that allows you to push a point into the stack. It allows you to pop a point from the stack. It allows you to ask who is at the top of the stack, what is a point that is in the top of the stack. And here we are changing a bit the rules from formal stack. In a formal stack, we don't have access to the second point in the stack. Here in this algorithm, I'll do this little change that will say you are allowed to see who is a point which is not in the top, but second of the top of the stack. That is, if my stack will contains, let's do a quick example. If I'm inserting P5, P3, P9, if I'm doing insert or actually doing push to the stack of these points in this order, P5 is the first one, then my first push of P5 into the stack will put P5 at the bottom of the stack. If I'll do pop right now, it will remove it. Instead, I'm doing push of P3. So P3 is standing now on top of P5. Adding P9 will be on top of P5. If I'm asking who is at the top of the stack, top will be P9, and the second is P3. Okay, any questions? People, how do I implement stack in whatever language you have in mind? Most languages, or, or you can use a library that has stacks, but if you don't have access to this library,
you could simply use a linked list for this.
Linked list is not a bad option, but linked list forces us to use pointers and dynamic memory allocation, and to ask a new point and delete a new point. It's not part of this course, but have you seen another application, another implementation, sorry? Linked list is absolutely fine. I'm sorry?
It just uses a function called stack.
Yeah, you can use a function called stack, and if you don't have access to this function, depending on your processor, if you have or you don't, you can use an array. How? Just keeping it as an array. Yeah, well, I have to decide at this point what is the size of the stack, and then at this array, call this array S for conveniency, then S of 0 will contain P5, and S of top, I'll have a variable called top, and S of top will contain P9 at this point. Yeah, so you can implement it using just an array. And as a rule of life, don't use a linked list if you can use an array, because it's way faster and it's much easier to debug and to optimize, and for automatic optimization and parallelization and etc. etc. Arrays are much more efficient when you can implement. Back to our algorithm. I saw the point. I'm just representing this. I'm just repeating the very same algorithm, Grahm scan. I still want to implement the same process of turn left, turn right, but I'm going to be more precise about how I'm going to interact with a stack. So I start by insert P1. I'll set the stack as empty, and now I'm inserting P1 and P2. P1 and P2 are in the stack, also a segment. Connect them, so as much as I know they are both in the upper convex hull, and you need to keep in mind that the vertex that I am, the first one to be deleted, or the first one to be executed, the one that I'm not sure about, is always at the top of the stack. The one that is going to, whose might or might not be chopped off, be removed, is at the top of the stack. But to know if yes or no, should I locate at it, I always need 3 vertices, which are Pj or Pi, the vertex under consideration at the moment, and the one at the top of the stack, and the second one from the top. Let's see how it works. So I inserted P1 and P2 to the top of the stack, and now for I goes from 3 till n. As long as the stack contains more than 3, if the stack contains less than 3, I need to check this condition again. However, if the let me check this condition again. Look at the orientation that obtained from the second condition. Sure. Look at the orientation that obtained from the second in the stack, the top of the stack, and the newcomer Pi. Pi, I equals 3 at this case, is not at the stack right now. And if you did a left turn, had you made a left turn when you went from where? to the second of the stack, to the top of the stack, to pi. At this case, who is the one that is going to be removed? Then do pop from the stack. And if not, just move to the next step, which is push of pi into the stack and move to I plus 1. Let's see how it goes. So, and ignore the condition, the size of the stack is smaller than 3. Ignore this part, only assume that this part is only one that happens. Okay. So what happened in this example? P3, I equal 3. I'm thinking about P3. I'm asking, is when I'm walking from the second of the stack, P1, to P2 to P3, did I do a left turn? Now I did a right turn, so it's safe to add P3 into the stack. The while failed because of the second condition. From P1 to P2, P3, I did a right turn, so P3 can be added, and in this case, the top, of course, and the second are updated. Let's insert P3, P4. Again, I didn't create anything bad, any left turn. P4 is inserted, and the top and the second are updated. Now I equal 5, interesting case, I equal 5. Now at this point we are going to use the loop a few times. Am I doing okay, actually this condition is fine. Okay, from P3 to P4 to P5, remember P5 is not in the stack yet. P4 is in the question mark. Did you turn left? Yes, you did. So perform pop. But we are still inside the loop. Now, if you removed P4, then do I have the animation? The top is P3 and the second is P2, going from P2 to P3 to P5. Are you doing a left turn? Still inside the loop? Yes. Another point needs to be popped, and only at this point I can insert P5 and to add it to the stack, and so on. And I didn't do the full animation for the remaining points, but you see how it goes. Okay, and when you are done, only at this point you can print. These are the point in the stack are exactly all the vertices of the upper convex hull. Can somebody please explain to me why, if the points are already sorted from left to right, assume that the points are already sorted from left to right, how much time will the whole process take? Like, naive argument will say that I'm adding n vertices, and for each one, the inner loop, the while, might cost n time. That's why the overall running time is order of n square. I mean, overall n square is correct, but remember, order of n square just implies the running time is not more than n square. It's a true statement, but it's true in the same way that you're in a balloon, as the old joke goes. It's true, but it's not necessarily giving you a lot of information about the algorithm. It's also true that this algorithm is order of 2 to the n. Again, it's correct. It's just not very informative. Can somebody give a better running time? Again, assuming that the points are sorted. Very good. And the argument?
Each time, like each element is only popped from the stack once, and it's
Exactly.
considered again.
Very good. A point might one point might cause a whole collapse, a cascading collapse of points from the stack. A point might be deleted addition of 1 point, which we have seen in this example, addition of 1 point might cause a lot of deletions from the stack. However, a point will be inserted to the stack only once. It will be deleted from the stack only once, and once it's deleted, it's never to be considered again. Exactly. I didn't get the name. Can you? Ryan, thanks. Yeah, thanks. So the overall running time that we did here in slightly more informally, sorting takes n log n. Let di be the number of points pop when we are processing pi. Then the overall running time is at each iteration 1 for all the operations that involve only pi, plus di will be how many times did I went inside the while loop and deleted point during the while. So the overall running time is sigma of 1, which I'm doing n times, plus sigma of all the di's. But what is sigma of all the di's? It's the total number of points that are deleted. But every point will be inserted into the stack once. Check out white, but every point will be inserted into the stack for sure once. But it will also be deleted, and some of the points will stay in the stack, the one in the upper convex hull. Some of the points, but the points that are being deleted, once it's being deleted, it's never to be considered again. So the sum of all the di's through the whole algorithm is at most n, correct? And that was the running time of computing the upper convex hull. And now we are repeating it for the lower convex hull again. So the only part that takes n log n is only the sorting of the points. Here's another version of a Grahm scan algorithm. It involves running the algorithm at this point, this version of the algorithm, this variant, I don't run the algorithm twice, once for the upper and once for the lower. Instead, I'm computing all the points immediately, and now I'm not going to sort them based on X or based on Y. Instead, I'll look at the leftmost point, find the leftmost point, and now think about the angle that the leftmost point sees each one of the other points. Think about the order at which the leftmost point sees each one of the other points, and now sort according to the angle. That is, if I think about it as a big pipe, a big telescope, or pirate-like telescope that I'm the leftmost point, and I'm going to sort the remaining points as I'm turning in my chair, going from left to right. So here will be my first point, P1, and now I sort the remaining points based on the orientation of the angle P1 to Pi. That is, it needs to be the order so that when I'm scanning them, it will be in the same clockwise or the same counterclockwise order. How do I compute this order, people? We said that we hate division operation. I need to sort all the points, and I can compute the exact angle of each one of these lines. But to compute the angle, I have to use operations that I prefer to avoid, which are namely division or arctangents, even less. Does anybody sees any other example or any other solution? I'm asking if I'm going from Pi to P1 to Pj, have I turned left, or have I turned, as a case from Pi to P1, from Pj to P1 to Pi, I'm going to turn clockwise. So the question is, any algorithm that you can think of has a case of if AI is larger than AJ, then you're doing one thing, or else you're doing the other one. In this case, you will replace the case of is one number larger than the other by checking, is this a clockwise orientation or is this a counter-clockwise orientation? So you can do it quite rigorously, this sorting process. Okay.
We check the y position.
I'm sorry?
We can simply check the y position for Pi and Pz.
I don't. Why? They are not all on the same. I mean, I can compute the intersection. You're right. I can compute the intersection of this segment with other segment, but that's again involved division operation. So, and if I have this order of the y points with these segments, then yes, it's just a y point. But if they are two segments, then it's just, once again, orientation inside a triangle. I cannot look at the y position of Pi and compare it to the y position of Pj immediately, because Pj might be above. I will not be able to distinguish between this case versus this case. Okay. It's not crucial. It's just, again, to get you used to think about, if we can do it more robustly, we should. But if we don't remember the formula and we need to compute it elsewhere, that's fine too. So I computed them in clockwise order, starting from the point in clockwise order. The leftmost one we'll see first, second, third, fourth, and from now on you are just continuing the very same algorithm, just left turn or right turn, and figuring out that the first segment and the last segment must be in the convex hull as well. So it's just another version of Grahm scan that might be easier or harder depending on how your input is arranged. Okay, it's just important to start from one point that sees, to start from the leftmost point. Okay, so consider the leftmost point, think about the orientation of the segments connecting the leftmost to all other points, sort based on the orientation, and apply Grahm scan once again, which is n log n. Okay. And I'll ask you in the homework, it has some pros, it has some cons comparing to the other variant of Grahm scan, which cares more about order by x, order by y. Here is a very different algorithm. It's inferior in terms of running time, but it's generalized to other problems, so I'll teach you this algorithm as well. Even though its asymptotic running time is the same, but it's definitely more complicated in the details and slower in the constant than Grahm scan. So, divide and conquer algorithm, which is in a sense a two-dimensional version of quicksort or merge sort. I have a big array of numbers to sort, so I'll split it into two smaller arrays, sort each one recursively, and now I need to merge my two solutions into one big solution. So the algorithm right here will say find the median x coordinate. Find the median, not the leftmost, not the second leftmost, not the nth leftmost, which is the rightmost point. Find the median point. That is a point such that half of the numbers are to its left, half of the numbers are to its right. I should have said something here about what should I do if the number of points is odd, so one of the set is larger by 1 than the other. It's noise and we will ignore it. The fact that one set is minusculously larger than the other doesn't change anything, not in the analysis. So right now I have two sets, all the points to the left of the median, all the points to the right of the median. Let's assume that if one such set contains only a single point, then compute it is its own convex hull and there is nothing to do. Otherwise, compute the convex hull of each half recursively. Call yourself recursively on each half. And now I want to ask, what does a convex hull of everything looks like? Can I state something about the convex hull of everything? How can I move from the two convex hull into the convex hull of the new shape? And for this we need to know what is a tangent, and we will define the tangent of a set. So tangent to a shape C is a line that shares a single point with C. And once again, I'll assume general position, so I don't have to worry about tangent that contains a whole edge. Now, if I have two convex shapes, for each convex shape, there are a lot of tangents, right? Through this vertex, I can find a lot of different tangents that all shares with this convex hull, call them C left and C right. I can share with each convex hull a lot of tangents. How many tangents do you see that are common tangent to both C left and C right? Again, how many lines can you find, at least in this example, that are common for both C left and C right? Help?
At least two.
At least two. But I can guess from my silence that
I think maybe four.
4. 4 is the right answer because here is 1. Here is another straight, kind of straight, not really line, that is another common tangent. These two are not really helping us when we are computing the convex hull. These two are crucial for us. This one and this one are much more important. The line that has the tangent that has both polygons C left and C right on its left on the same side, is either from the left or from the right. By the way, how many common tangents do you have if the shapes are allowed to intersect? If C left and C right have points in common, how many common tangents can they have? if they are both n-gons, let's make it, let's keep it under control. If they are both, if each one is n-gon, then there can be a lot. But if everybody agrees, I can have this as a common tangent, this as a common tangent, this one, this one, this one, this one, etc. I'm only limited by how many vertices. So I can have n tangents out there, but once two polygons are don't have a point in common, there could be only 4 common tangents, and we care about the common tangents that have the 2 polygons at the same time. Why? Because once I know what are the common tangents, I know exactly what is the convex hull of the big shape of all the points. So let's ask, how do I, what? Because now if I find the common tangent, that now the convex hull will consist of the part of the left polygon between the common tangents, concatenated by the new edge, concatenated by the right part of the right polygon up to the new tangent, concatenate with a lower new tangent, and that's exactly the new convex hull. And it will take me linear time to do it. So once I'll show you how to find this common tangent in linear time. But once I'm doing it, what is the running time that I expect? Well, it just behaves like merge sort or quick sort, which is what's a running time that describes both of them. You're spending t, if t of n is a running time of the algorithm on n points, then how many points do I have on the left side? Remember, I picked the median, so to the left of the median I have n half many points. To the right of the median I have n half points as well. So you're getting t of n, which will be the running time of computing the result for n points, would be t of n half, let's say, ceiling on the left part, plus t of n half on the right side, plus some constant times n, which is the merge stage. But now I said that ceiling and floor don't play a role in the running time, so we'll ignore them and just write both of them as n half and n half. So you're getting 2 t of n half plus c times n. And if you have seen recursion formulas before, that's great. If not, then there are very few of them that we need in this course, and this one, which is quite popular, that will I'm going to describe to you exactly how do I get to the running time, to the solution of this formula. But so what is the overall running time of the algorithm? I'll think about a way to visualize the overall execution of the algorithm. And a way to visualize the overall execution would say, what stages does the algorithm do? If you think that the merging of the 2 polygons takes constant, I don't care, I don't know, but a constant times n to perform the merging stage. I still owe you to show you how, but trust me. But if it takes a constant for the merging part, finding the 2 common tangents and go through the vertices and relabel them, what is the overall running time? It's a merge step plus a recursive call for the left part, t of n half, recursive call for the right part, t of n half. blinking is t of n half, let's write it explicitly. T of n half is nothing but the same constant times the merge of just the left part, which is c of n half, plus the merge part of the right part, which is c of n half, because that's how many points it has, plus the recursive call t of n over 4 in each subpolygon, etc., which in the same way of visualization, this consists of c of n quarter in each quarter of a polygon, and so on, and you continue with this tree. And again, it's not a search tree. It just tries to show you what are you wasting time for in the execution of this algorithm. So when do you stop with this partition? Start with n half, n over 4, n over 8. At the end, you have, after log n many steps, you end up with vertices with sets of size 1. Set of size 1, there is nothing to partition. We just say it's its own convex hull. That's why vertices there are. That's why we stop with vertices of size 1. Now, so the height of the tree is log n, and let's sum up the running time by level. In the topmost level, I spend c times n for the last merge sort. I also spend c of n half for the merge of the left part, plus c of n half for the merge of the right part. This plus this equals c of n once again. What about the merges of the quarter polygons? C of n over 4, 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 sum them up, end up with C of n once again. And so on for each one of the levels, and that's how you have n leaves. So that's how, if you sum up the running time in each one of the levels, you end up with n log n as the running time of the whole algorithm. Okay, so that was the part where we also did a check mark on this course as fundamentals to algorithms, one of the topics of algorithm of introducing to divide and conquer. In refreshing the partition of the running time, let's now explain how I can find a common tangent. So first I want to convince you that if I have a line that goes from A and to a vertex V of the other polygon, the point A is from outside edge of B, V is a vertex of edge of B, I want to convince you that if I know what is a convex hull, and let's define exactly what do I mean by knowing the convex hull, meaning I know what are the vertices on the convex hull, because there might be points inside the convex hull that are not vertices. So A, I know what are the vertices, and B, I know at which order they are. I know for each vertex who comes next in a clockwise order, who comes before in a counterclockwise, in a clockwise order, well, before and after in a clockwise or counterclockwise. How can I check if this line that goes through V is a tangent or not? Well, since edge of B is convex, all I need to check is, let's check the vertex just immediately before, and let's check the vertex just immediately after. If they are both on the same side of this line, then the remaining of the polygon is also on the same side of this line, right? Because, proof by example, it cannot be that my line from A to V, that this polygon has mingle up and intersect this line, once again preventing L from being a tangent to V. That is, it's enough to just check V, the V minus and V plus. The two vertices just before and after. How do we prove something like this? Formally, for example, in the homework, we remember that a convex shape also implies that it's the intersection of all the half planes that defines it, for example. It's one way to start such a proof. So if it's enough, in particular, in constant time, I can check if the line through A and V is this a tangent of A of B or not. Now, if you have this assumption, here is now how I can find a common tangent. I'll start when A and B are the rightmost point of the left side. A will be the rightmost point on the left side, and B would be the leftmost point of the right side. Example, when this is HF, this is HB, I will start when A is the rightmost point of the left side, and B will be vertex 3, the leftmost point of the right side. Let me go back one slide. After I initialize A and B, what do? Well, as long as the segment AB is not part of the lower tangent that is common tangent to both A and B, if the segment AB is not the lower tangent of A, then do A equal A minus 1, which means move 1 point clockwise on A. If and you might repeat it a few times over here. If AB is not the lower tangent of HB, do move 1 point counterclockwise on the other side. And the order that you'll do it doesn't really matter. And what's interesting here is that you never overshoot. You never have to come back. Let's see how it works. Proof by example. I'll start when A and B. Here are this is A, this is B, and I'll start. I'm checking if maybe this segment is by itself a common tangent to both. Is this a tangent to edge of A? It is not, so I am walking clockwise on the right side, setting A equal A minus 1 if the vertices are in counterclockwise order. And maybe I'll have to walk, next I'll walk and at this point I am, let me go back one slide, at this point I am a common I am a tangent. AB is a tangent to the left side, but it's still not a tangent to the right side. So I'll walk on the right side. Again, how do I know that it's not a tangent? Just check for with respect to for the vertex one above, one below, the next and the previous. Well, it's still not the common tangent, then keeps on going. And etc. And at the end, you are done. It's interestingly that as you are moving more in one polygon, you might have to walk more on the other. The order doesn't matter. You might have to do a few steps on the left, then a few steps on the right, and a few steps on the left again. But you'll never overshoot it. You never have to go back, implying that the whole process takes linear time. Hence, it's an n log n time algorithm. And it takes a bit more time to convince that I'm not lying here, but essentially that's all in it. And that's how divide and conquer can help us reconstruct the convex hull. Questions? Okay, we are almost done with convex hull. We just have the lower bound that will show that you cannot do better than n log n. We'll also talk about gift wrapping, which is inefficient but an example of output sensitive, and then moving into DCL and line sweep algorithm. You have the slide online accessible from the course website. Thank you.